Alright guys, next one is the Y to Y configuration. I did notice on the previous videos that they were a little bit small when I was looking on my phone. So hopefully you're able to see these a little bit better. Hopefully this is zoomed in a touch. Okay, so starting off with this guy, we have the Y to Y configuration. So we're going to do our primary here. And again, if you've watched the other videos, then you can see that we're doing the primary on this side. Then we'll use this diagram in order to wire up the diagram below here. So with this guy, we're going to feed line 1 into this terminal right here. We're going to have line 2 coming into this guy, and then we'll have line 3 coming in here. Okay, these labels right here on our primary are going to be H1, H2, H1, H2. So all the 2's are tied together at that common star point, and then we're going to feed each of the H1's from one of these terminals on our line conductors. Okay, if we take a look at here, let's throw in the common core. There was a question on one of the other videos on what I mean by the common core. The common core is the piece of steel that the primary and the secondary are wound around. So there's this pieces of laminated steel that are all pressed together. They're not part of the electrical circuit, they're part of the magnetic circuit. So the way that the primary transfers the energy to the secondary is through induction, and the common core really helps for the efficiency of that transfer of energy. Okay, so we need to throw in some voltages here. Okay, so again, in our shop, we have 208 volts. That's our line value. Okay, so that's applied to line 1 to line 2, line 2 to 3, and from line 1 to line 3. Okay, so we have 208 volts, 3-phase going in. And as soon as we connect this star point right here where all the 2's are connected together, that means that our phase voltage, or the line to neutral voltage, even though there's not a neutral here, but the line to that center tap right there, ends up being 120 volts. Okay, so the relationship on a Y is that your V line is equal to your V phase times root 3. Okay, so if you're taking that equation, then your V phase is equal to your V line divided by root 3. So 28 divided by root 3 gives us 120 volts on the phase. Let's use that in order to wire the primary here first. We've got line 1 going to H1. Come on. Okay, and all of our 2's are going to be joined together. So this guy is going to go to this center point right here, but it's not actually connecting outside of the circuit, right? I didn't bring 4 wires in. I only brought 3 wires in to that circuit. So I'm not going to bring that to the neutral because I didn't provide a neutral there, but I am going to tie all of those guys together. So all of the 2 conductors are going to be jumpered together so they're at the same potential. Okay, but I didn't bring a neutral into the primary there. I brought in 3 wires, 1, 2, and 3, corresponding to these guys. Okay, each subsequent transformer is then fed from the next line, right? So the second transformer is fed from line 2, and H1 on the third transformer is fed from line 3. Beautiful, okay? And then we said that our voltage on the outside was 208 volts on the line. Again, same voltage all the way through. And I'm nearing the end of these videos, but let me know whether you can see this properly on all of the devices. Like if you're watching on a computer or a tablet or a phone, let me know whether you're able to actually view everything properly. I checked the audio, it seems all right, but I'm just not sure if you can see the fine details of the video. Okay, so that takes care of everything on our primary there. So remember that the ratio here is 1.73 to 1. That's the ratio of the primary conductors to the secondary conductors. So with this guy, normally on all the other videos, we had 2.8 on the line and 2.8 on the phase, right? Because we're dealing with deltas on the primary. But now we've got 120 volts on the phase. So if I take 120 and I divide it by 1.732, that gives me 69 volts on the secondary. So now we're going to get into some funky voltages. So because of the ratio of 1.73 to 1, which has nothing to do with three-phase or anything. It's just to do with the physical number of turns here versus the physical number of turns here. Then I get root 3 less over here, and I get 69 volts. 69 on each of these guys on the secondary. Okay, so we're definitely going to get some funky voltages coming out of this guy. So doing our diagram on the secondary side here, we're being asked for the lower voltage, which we said is the parallel connection. Okay, so now we're doing a Y secondary. Y to Y transformers are not used all that often, like in our normal distribution. Normally, like on the previous video, our bread and butter is the delta to Y connection. You are going to see Y to Y transformers. I've seen them on solar panel installs where they've gone, the solar panel output is 277 480, and they want to change that to 122.8. So they'll use a Y to Y transformer. So in some machinery or in some installs, you will see a Y to Y connection. The issue with Y to Y transformers, from what I've read, is that harmonics can pass between the two primary and secondaries because they do have that common connection on the neutral there. Sometimes from what I understand, the primary and the secondary are bonded, and so bonded to ground, and so you can have harmonics passing through these units. So our voltages on the outside, well, let me finish off this guy right here. So this guy is going to feed line 1. I had line 2 feeding the primary on the left-hand side, so I'm going to grab line 2 over here, and then line 3 is going to come out and feed this guy right here. Then we do have the center tap right here, and that's going to be our neutral, and then that again is usually bonded to ground. Okay, our voltages here were 69 volts on each of these guys. A little bit of dyslexia coming through, sorry, hang on. Beauty, and then we need our labels on the transformer, right? So this one is X1, X2, X3, and X4. So this is the same diagram as we did before for the secondary, but now we've got different secondary voltages. Beautiful. Okay, so let's use that. I'm going to wait to do the line voltage because I want you to think about like what's the line voltage. There's 69 volts from line to neutral, so what's the voltage from line to line on the output here? But let's do this wiring here first, and then we'll see if we can determine what that voltage is. Okay, so we are jumping X1 and X3 together, and X2 and X4. That creates that parallel connection that we've seen in all the other videos. Beautiful. This center point here, we are going to bring out to the neutral. So for my first transformer, I am going to bring that guy out to the neutral here. But we need to make sure that all our 2s and 4s are brought to the same potential there. So we'll do that in green here. So that bad boy is coming out and feeding this guy. Again, you don't have to bond this to ground in the shop because it's not really going to affect your labs or any of the voltage that you see because we don't have any physical loads connected to here. But normally on a Y, we would have bonded that neutral to ground. Okay, and then we need to bring all of these bad boys to the same, come on Pete, to the same potential. Okay, hard to keep these diagrams nice and neat. Okay, so now we're all at the same potential with our 2s and 4s, and they're being brought down to this neutral connection here. Okay, then each subsequent transformer, again, if we label these guys with transformer 1, 2, and 3, and these would be the secondaries, 1, 2, and 3, then the first transformer, X1 and X3, is going to feed line 1 out. Then the second transformer, X1, is going to feed line 2 out. And then the third transformer, X1, is going to feed line 3. Beauty. Okay, so now it's a question of what the voltage is from line to line here. So if we have 69 volts from line to neutral, then what do we have from line to line? Well, we would have 69, and then we would multiply that by root 3, and that gives us basically 120 volts out. So this one's funky as well, in that this voltage right here is 69 volts on the phase from any line to neutral, and this voltage right here is going to be 120 volts on the line. So for this transformer, or this configuration that we've created, we've got two 8 volts, 3-phase in, and then on the output, we're going to have 69 volts from line to neutral. That's our phase value. And then we've got 120 volts from line to line, and that's our line value. So between these guys, 120 volts on the line, these guys, beautiful. And then from any line to neutral, we're going to have 69 volts as our phase value there. So some funky voltages that you'd never see out in the field. And the reason why we're getting those voltages is simply because we only have one source voltage here at 2.8. Okay, so we'll pause the video here, or you can pause the video here. Make sure you got all the information. So if you're doing this on the test and you're writing everything out, because you'll have a blank sheet of paper and we'll just say, all right, give us a diagram for the delta to Y or the Y to Y. And we're looking for everything. We're looking for the diagrams above. We're looking for line voltages, phase voltages. We're looking for ratio of the transformers. And then in the secondary, we're looking for all the appropriate connections and line and phase voltages as well. Beauty. Okay, let's move on to the next one. Same configuration, Y to Y, but again, we're going to do the high voltage connection. And before I move on, there is something here that I can see that can cause confusion as to the way that I've done this. So I didn't make use of this neutral because in our shop, we don't have a neutral on our transformer stations. We just have 3-phase coming in. So for us, in order to create that Y, we're just going to tie our H2s together. But normally on either side of this transformer, this center point is often bonded to ground, both on the primary and the secondary. There's lots of discussion as to whether it's always bonded to ground on primary and secondary, whether it's just bonded on the secondary. But I can see that I may have caused some confusion here in that I didn't make use of that connection and I didn't show that being bonded to ground. So just to clarify things, in that out in the field, oftentimes you are provided with a 4-wire input to these guys, and our connection here for our neutral would have then been from the same thing from H2 to H2 to H2, but that would have tied into this neutral conductor, and then that neutral conductor would be bonded to ground primary there. So didn't want to that may have caused confusion in itself, but in our shop we only have line 1, line 2, and line 3 off of our 4-amp breakers. We don't have a neutral available. So for us, in order to create a Y, we're just going to jump our H2 to H2 to H2. But out in the field, you may have a 4-wire coming in and a 4-wire coming out. And both sides of the transformer, both the primary and the secondary, will be bonded to ground. And that's how, from my understanding, that's how the harmonics are transferred, because then you have a common connection, electrically common connection between the primary and the secondary. So it's no longer just magnetic fields that are transferring from primary to secondary like you would have on the delta to Y. Now you've got a common connection on that ground where harmonics can then pass through this transformer. Okay, let's move on to the higher voltage now. Hopefully I didn't cause too much confusion there. Primary is identical. So if you want to pause the video right here and do your diagram for the primary, it's identical. We're having the three lines coming in. They're each feeding H1, right? And we said these guys, we're labeling these guys A, B, and C on each of our diagrams. Okay, and H1 was being fed from line 1. H1 on the second transformer was being fed from line 2, and H1 on the third transformer is being fed from line 3. So what I'll do is I'll do the same here, where the neutrals are going to be tied together. So all of the H2s are going to be tied together. And I'm going to, on this diagram, I'm going to bring that up to this neutral, and that guy is going to be bonded to ground. But just keep in mind that in our shop, we don't actually have a neutral on our feed. So you're just going to jumper all your H2s together there. Okay, everything stays the same in that the voltage on the phase, if we have 2.8 coming in, so we have 2.8, come on, 2.8, 3-phase coming in. That means that our voltages here are identical to the previous diagram. And that gives us 120 volts on the phase. So you can see up above on this diagram, we still have the 120 volts there. Okay, so I believe that's everything for our primary circuit. Now we got to do the secondary. We're doing the higher voltage, so we're going to do a series connection of our windings there. Double windings on the secondary. Beautiful. Line 1 would be fed off of this guy. Line 2 we'd pick up off that corner. And then line 3 is going to come off this guy. Okay, this one is bonded to ground as well. And we need our labels here, X1, X2, X3, and X4. X1, X2, X3, and X4. So all the 4s are being tied together on the secondary, and in order to get the higher voltage out of those secondary windings, we're going to series up 2 and 3. And we saw on the previous diagram that because the ratio is 1.73 to 1 ratio between the primary and the secondary, if I have 120 volts on the primary, that means I'm going to have 69 volts on the secondary windings here. Beautiful. Okay, so we'll throw that into this diagram right here. Nice. So our neutral here, let me do this. Let me move that neutral over here because I usually had it coming out over here. So that's our neutral, right? And that is bonded to ground. Then the voltage between any line and neutral is now going to be the sum of 69 and 69. So this voltage is going to be really strange. It's going to be 138 volts on the phase from any line to neutral. Okay, the same rule holds true in that the line voltage is going to be our phase voltage times root 3. Phase voltage is now 138 volts. So we take out our calculator, 138 times 1.732 gives me 240 volts output. So our line to line voltage is going to be 240 volts. So I warned you, we're going to have some strange voltages coming out of here. Okay, I think we got everything on that diagram. Let's finish off the diagrams below here. Okay, so we've got 2 and 3 that are jumpered together to create that series connection. Okay, line 1 is going to be fed from x1 of the first transformer. Line 2 is going to be fed from x1 of the second transformer. And line 3 is going to be fed from x1 of the third transformer. Okay, and then we need our neutrals tied together. So all of our 4s are going to tie together, and they're going to feed that neutral bus there. That neutral bus is also bonded to ground, and we need to grab all of these guys and put them at the same potential. Beautiful. Okay, so our output voltages, we'll add that to our diagram here. So our line voltage here, we just found to be 240 volts from line to line. So we got 240 volts, 3-phase coming out. And we found that the line to neutral voltage was 138 volts. Again, would you ever see 138 volts out in the field? No. We're just seeing those voltages simply because we only have one voltage to work with in the shop. Cool. So output here would be 138 from line to neutral, and we'd have 240 volts from any line to line value. Excellent. I think we've got everything on the diagram there. So that finishes up the next project that you're being asked to do in the shop, right? I can't remember which one we asked you to do, whether we do the low voltage or the high voltage, or whether they're asking you to do both. Now we've got both diagrams, and you should be able to bang off each of these guys. And then hopefully the voltages that you're seeing on the meter are matching what we see on the screen here. All right, guys, we'll see you on the next one. Next one is going to be the Y to delta. So the one configuration that we have not done yet is going to be the Y to delta. We'll do that on the next one. Thanks, guys. See you soon.